I want to stress upon the fact that mass spectrometer is not a separation technique. It is an identification technique. So the better your HPLC method is, better results will be you will be get on LCMS. So that is very, very important. If there are 2 or 3 components that goes into the mass spectrometer will give you the values corresponding to the mixture of 3 compounds. So it cannot analyze, it can separate ions, but it cannot separate your compounds. So if you have a mixture of 2 compounds going into the mass spectrometer at the same time, and it gives you 2 molecular weights, you can say that, yeah, it's a mixture of these 2 compounds. So it can do an ion separation, but it is not cannot do a physical separation of your mixture. So this is a very important basics before we start. Now this is very important for you to know. This is, I would say, molecular space. If you are going to plot the total organic molecules in what is available today, you will say that they go from non-polar to very polar compounds and mid-polar compounds, and also from low molecular weight compounds to very high molecular compounds. So when you see this, you see that a small portion of this here, which may be 5% or 10% of the molecular space, are amenable to GC and GCMS, because the condition for GC and GCMS has to be, they have to be volatile, they have to be thermally stable. They cannot decompose. These are very important things. Though a few compounds, as I said yesterday, you can derivatize them and to form some of the derivatives where you can do the GC and GCMS. But their compounds are also very few. But if you take this entire space over here, they are high molecular weight compounds and high polar compounds, and that requires techniques such as electrospray and generally LCMS, because LCMS deals with high polar compounds and with the high molecular weight compounds, and including compounds which you cannot heat, the proteins and peptides. At one time, we were not even thinking about doing mass spec for proteins and peptides, but today it has become very, very common to do the mass spec for proteins, peptides, enzymes, etc. So it has taken a tremendous amount of position in the analytical industry, where many people are using, majority of the people are using LCMS rather than GCMS, because the applications is very wide, especially biochemists who never dreamt about a mass spectrometer before in their analysis, and now the biochemists cannot live without mass spectrometer. So what are the few advantages of a liquid chromatography? You have listened to the liquid chromatography, and that is analysis of labile analytes. You cannot use them for in GC, but HPLC is very good. Analysis of more polar compounds without derivatization, analysis of significantly higher masses, which I mentioned to you, and reduction of lengthy cleanup. You can do a guard column, etc., and you can really remove a lot of dirt, and you can let the sample into the LC. And there are advantages of the mass spec, because as I told you yesterday, the mass spec is a identification technique. So you can get structural elucidation, you can get an idea about the structure of the molecule, and then if you do an MS/MS, you can reduce your cleanup. When it comes to the MS/MS, when I talk about the triple quadruple MS, I'll be able to elaborate on this very much. And specificity, as I mentioned to you, it is very mass specific. So if you want to identify to see whether your compound is present, then you really put in the mass of that molecule, and you will be able to see whether it is present or not. So that is the specificity in a mass spec. As I mentioned yesterday, if you are looking whether cocaine is there or not, you just put the ions of cocaine 303, 182, and 82, and it will tell you whether it is present or absent. And that is the specificity. The amount of specificity that you get in mass spec, you cannot get in any other technique. That's a fact. And there are different modes of mass spec LCMS, and that is what we will be talking about. What are the different modes and how do we operate them in different modes? So this is a very important session, and I hope you stay with me today so that you get the best out of this presentation. Yesterday I showed you something very interesting. This is the GCMS system. So don't think this is the LCMS. I am just reminding you what we did yesterday. Yesterday I showed you the ion formation, ion separation, ion detection. So this is the ion source, quadruple analyzer, and then you detector. This is when then you have the high vacuum system. It is a similar concept in LCMS also. For different types of LCMS, we have some modification, and that is what I am going to talk to you. The next few slides are going to be extremely important if I want to take you forward with me today's seminar. So This is the liquid chromatograph from liquid chromatograph. Now, what was the challenge in making an GCMS was so easy. What was the problem with the LCMS? LCMS was that if you have, when you are having a 1 milliliter flow rate, and when you put into the ion source in in a vacuum system, you can see that gets into a 1 milliliter can become 27 liters or 30 liters or more, depending upon the solvent. And that is something that the pump cannot take up and the mass spectrometer will fail. So initially what they did was there was a liquid chromatograph and a very small amount of liquid was sent into by direct liquid injection or particle beam, thermospray, dynamic fab, etc. There were some of the techniques that were being used before, and I have used all these things. This was only available to me before I started using LCMS, which is the latest today LCMS. So these are the initial ways that we were doing LCMS many years ago. So you had an ion source, mass analyzer, that is electron multiplier detector. And the problem was we had only single quadrupole, triple quadrupole, and maybe some 3D trap. But today, the type of mass analyzers are so many, and the detectors are low sensitive. And today we have very high sensitive detectors. We have much better liquid chromatograph. We have even nano HPLC that you can connect to the LCMS. LCMS does not like very high flow. So you have to have low flow in LCMS, 1 milliliter or less. If you are going to nanoflow, it is too less, so we may modify it by adding a little bit more solvent front before it goes to the mass spectrometer. So there are many optimizations that you have to do in mass spectrometer, in LCMS. And also you will see at the bottom, that when the start of the LCMS, people said that LCMS does not have much big market. Then in that case, many companies want to invest in LCMS, so they will have very few manufacturers and less competition. Whereas if the market improves, if it becomes big, then everybody wants to have a piece of the pie, and there will be more manufacturers of the technique, and that is very important. That is why I say in analytical industry, you need to have a very severe competition. If you don't have competition, you will get substandard materials. So the competition is very useful in analytical industry, so that you can pick and choose, and every competitor is working hard to make sure that they make a better instrument than the other one. So that is the advantage we have when there is a competition. Now, when you get the latest mass spectrometers, as I said, you have choice of pumps, choice of columns, good literature, knowledge base, training. All these things are available today to you. So it is the best time, the right time for everybody to be involved in LCMS. And what are the main criteria here? They are all called as atmospheric pressure ionization, and in electrospray, APCI, APPA, these are the three variants of ionization techniques that I'll be talking. Now, when you look at this slide, which is very interesting compared to the previous slide, is that the ionization source is outside the high vacuum system. In the high vacuum system, you have the mass analyzer, you have the quadrupoles, 3D and 2D traps, and you have time of flight, you have all the hybrid mass spectrometers, and you have the orbit trap, etc. that I was talking to today. So you have more types of analyzers today, and you are, because of that, we call them different types of mass spectrometers, and you have very high sensitive detectors also. And only the mass analyzer and the detector is under high vacuum, and you have much more powerful computers and the software also. So today you can say that the LCMS has come of really age for the last few years, and we are able to get the greatest potential of the LCMS for our use and applications. So the applications of LCMS has really widened, right from the small molecules all the way to the macromolecules such as proteins, peptides, and the enzymes, etc. And if you see today a mass spectrometry journal, you will be surprised. There are more applications to biochemistry than into small molecules. Small molecules, you can deal with the GCMS or LCMS, but in the case of the high molecular weight compounds such as protein, peptides, etc., you cannot heat them. So the only way you can do is by LCMS. And the advantage of LCMS is also that LC is a very versatile product, a versatile instrument, and you can have different column selections. There are hundreds of column selections today in sizes, in terms of the stationary phase, and in terms of the amount of liquid mobile phase you want to do. So you must remember that LCMS, in the LC, when you use these solvents, some of these mobile solvents can be very expensive. So one of the advantages, one of the challenges is that how do I reduce the flow of this mobile phase? So there are HPLCs with the smaller diameter columns and a smaller length columns, but with the same efficiency that you will get with the bigger columns. So that is the way it has really improved. And that is why you have the HPLC and UHPLC, etc. So instead of the 3 micron to 5 micron particles, today they say sub 2 micron particle, 1.7 nanometer particles. And these are very, very useful to you. They are 1.7 micron particles, and we call them, nano HPLC. So this, and also you can go to nano flow rates. So instead of using milliliter quantities, you can go to microliter quantities, etc. when you are using HPLC. So these are the advantages today have, and you have very good competition for technology and quality. So today, the type of mass spectrometer that is sold to you, they are all very good. They will do the job that you want to do, and there is no excuse for the work saying that I don't have the equipment, so I am not able to do. So that excuse is no more valid. So let's see what are the types of, how do we move forward. Oh yes, I am very, very happy to share this picture with you. This is extremely close to my heart. Today's talk is going to be on electrospray, and it is a very important time to remember Nobel laureate Dr. John Fenn. And he is the inventor. Dr. John Fenn is the inventor of electrospray mechanism, and he deserves all the merits. And what we owe to him a lot, all the future generations will owe a lot to him for inventing the electrospray mass spectrometry. And he established this, he founded this technique in 1988, and he was awarded this Nobel Prize for this in 2002. And I met him in 2007 at the ASMS, I think in Minneapolis, and he breathed his last in 2010. So I was one of the lucky people to meet him, and he was very happy to pose for a photograph with as many people as they wanted, and that is very high generosity from him. And he gave an excellent lecture, as whatever lecture he gave, at the Nobel laureate when he received Nobel Prize winning day, he presented the same thing at the ASMS. So I could listen to him, and really he's like the god of electrospray mass spectrometry that I'll be talking to today. I'm very, very happy that I could be with the inventor. I am probably stressing a little more than what I should do, but that is only an emotional aspect of it. Commercially available LCMS systems. Again, this is only alphabetical order I am always putting. This is not in any sequence of preference. So please remember, I am not promoting any instrument at all now. This is the Agilent LCMS, and this is the SciEx LCMS, and this is the Thermo LCMS with the HPLC. Here the HPLC has to be added here, and this is the Waters, the HPLC. Here the HPLC is already there, and the mass spectrometer. So that is very important. I think this is the acuity, and so once you add the LC here, you can add any LC because SciEx does not make, I think, an HPLC machine. So you can add any HPLC that you want over here. But Thermo has their own HPLC, Agilent has their own HPLC. So I'll be talking about the types of ionization and sources. One is the electrospray ionization. Again, I'm talking about atmospheric pressure ionization. Now, what is beautiful about this? I will go back. Probably I missed to say something about this. Why do you call this atmospheric pressure ionization? I made it very simple to people. They say, oh, I am very much scared about atmospheric pressure ionization and electrospray and all that. I made it very simple. It is nothing but ionization under atmospheric pressure. So I deflate the balloon. There is nothing to worry about it. Atmospheric pressure ionization is nothing but ionization at atmospheric pressure. Please remember that, and you can see that the session becomes very simplified for you. So today I am going to talk to you about electrospray ionization. I'm going to talk about atmospheric pressure chemical ionization, atmospheric photo ionization. Now, electrospray, why do you have these type of things, different type of ionization? You need different type of ionization because there are always some exceptions to the compound. Electrospray ionization, you can say it is a nearly universal. It will work for low molecular weight compounds, low polar compounds, and high molecular weight compounds, and high polar compounds, and also to biomolecules. So electrospray is the most common, the most popular atmospheric pressure ionization techniques. But there are some compounds which are always followed, say that, no, we are not amenable to electrospray, we won't agree with you, we won't ionize under those conditions, we need a little bit more stringent, we need a little bit more beating in order to ionize. So we will beat up that ion, and we will make sure that it is ionized. So that is atmospheric pressure ionization. And still there are some molecules say we are not amenable to this also, we need something else, and that is the atmospheric photoionization. So different techniques are available to us. We are very lucky today that we have the ability to use all this ionization depending upon your type of organ, the type of samples you have. In most of the organizations that I will say, in general, this is a must. Electrospray is a must. Can work with the low molecular compounds as well as high molecular. So when you are going LCMS, please make sure that you have an electrospray ionization, otherwise don't buy an LCMS. Then atmospheric pressure ionization can be an accessory, and this can be an accessory. Depending upon what type of compounds you are analyzing day in and day out, I'll be able to explain to you what are the compounds that will work very well with electrospray, very well with this, and very well with this. So that will be the clarity that will be giving to you today. So atmospheric pressure ionization has revolutionary LCMS open to a wide array of applications. Dissolution ionization analyte occurs at atmospheric pressures. Gas phase ions are sampled by the high vacuum mass spectrometer. Don't worry about these statements. This is what I am going to explain to you. Okay, here is the explanation. Now, from the HPLC, your whatever is coming out from the tube, it is connected to the ion source. There is a needle here, and which is a bilayered needle. That is bilayered needle with a very, very small orifice here. Okay. So what it is going to do is that this needle you can have in any orientation. Now these are 90 degree, you can have to 5 degree. Do not have it 0 degrees because it will directly get sucked into the mass spectrometer. You don't want that. So this you will see either in 90 degree spray or something like a 5 degree spray where the solutes and solvent doesn't go directly into the mass spectrometer. So this part is in the atmospheric pressure. Okay, and this is going into the, when you go into that, it is going to the high vacuum system, mid vacuum and high vacuum. So in the ion source, what happens is this is a small orifice also, and here there is a small tube here. The idea is that when it is sprayed from this nebulizer, this is a very, very small internal diameter, and it's a bilayer needle. It's a bilayer needle. So through the outer needle, outer layer, you get the nitrogen gas, nebulizer gas, and through the inside one, the liquid comes out from your HPLC. Please listen to it very carefully. Through the inside one, the liquid comes out of the HPLC. HPLC tube will be connected to this nebulizer, this bilayered needle. And from the outside of the needle, there will be gas which is flowing at several liters. So when it comes out, this is like what you see a perfume, this one, you get very, very micro droplets. You get the droplets here. And then what happens is when you get the droplets, the idea is that you have heated nitrogen gas coming from here. The idea is that the droplets get drier and drier. They become smaller and smaller. This is a very important mechanism that you have to follow. Now, this is an ion formation happens here. And the reason is that they keep you can see dielectric capillary reductance. They create a difference in voltage. About 5000 kV plus minus is applied between this needle and here. And in that, that current, you will see that the molecules get ionized. So the ions are present in the molecule. So this is very important. This is a solution chemistry. There is no electron bombardment. This is what I said yesterday, that it is important to attend the GCMS session if you have to understand this better. There is no electron bombardment at all. There are no filament. There are nothing. This is happening. Ionization is happening at the atmospheric pressure, right when the sample comes down from the needle, when it gets sprayed, and then you have to do a little bit of solvent chemistry. I will talk to you about the solvent chemistry later. And then your solutes which are surrounded by the solvents, they undergo an electrostatic current between the needle and this main frame, and that will be around plus minus 5000 electron volt kV, not electron volt, kV, and that electrostatic force, when you have it, then the ions are formed inside the spray. That is inside this. Now the idea is you have to dry this what you call as droplets, and make sure these are liberated, ions are liberated, and ions are sucked into that. So if it is a positive ion, then we create a negative ion voltage here, so negative potential here, so the ions are sucked into the mass spectrometer. So it is a sucking, whereas the neutral one and the solvents do not get sucked into the mass spectrometer. So you apply a negative voltage in the way that all the positive ions get sucked into the mass spectrometer. So this is the beautiful way that this is done. I have to stress upon it once more. This is a solution chemistry. So you have to use the solvent front in such a way that when you have the liquid coming from the HPLC, that it is sprayed as a very as an aerosol spray, very small droplets, and there is a potential difference that we maintain between the needle tip and this frame here, and that's about plus minus 5000 kV. And then in that, depending upon if your ions that you want to form, positive or negative ion, you will change the voltage potential plus or minus, and then you will form the ions inside the droplets. The ions, your solute ions, are formed inside the droplets. Now your job is to dry these droplets and make sure that the droplets, the vapor of the solvent phase and everything, all if you are using some of the salts, etc., they are all pumped down, and you have got only the ions which are sucked into the mass spectrometer. And there is a difference in the potential negative voltage here, so the positive ions are sucked into the mass spectrometer, and all your wastage of gases, all these gases are pumped down by the pump. So that is very important for you to understand, and this is the way it looks like. It becomes a little bit more easy here. So you see a potential of plus minus 5 kV is attached, and this is the sheath, we call the sheath of the gas sheath. This is from where this is an exploded diagram. As you can see, this is the needle, bilayered needle. Air comes from there, nitrogen comes from here, and then liquid sprays from here, and this is what is called a big plasma that you can see of all the ions and the droplets here. And our job is to make sure that we dry them. Now when you dry them, there are different processes, and this is an actual mass spectrometer inside a photograph taken. I'm very happy to show it to you. You can see it in some of the journals also. So it is spraying, as you can see, and lot of spray, and the salts and everything will stay outside the mass spectrometer, and the ions are sucked into the mass spectrometer. So this is the part of the ion source. As you can see, this is the part of the ion source, and so the ions are sucked inside. Okay, and this is the bilayer needle, as you can see. So it is very important for you to see these things, and I will move to the next slide. So once again, what you see here, this can be in different angles. It can be in this angle, it can be in this angle, it can be in this 5-degree angle, but never exactly onto this angle, because if that is the case, the spray completely will go into the orifice. This is also a small orifice, and as I mentioned to you, this is applied, there is a negative voltage, so this part of it sucks your ions into the mass spectrometer. Okay, so this is what it is showing. As I showed you, there is a potential difference that they can maintain between the block of the ion source and the needle, and then these droplets are coming out here. So the drop, as you can see, contains a lot of ions. As you can see, we are not interested in the negative ions. Negative ions will not be sucked into the mass spectrometer, and there is a drying gas which is coming, and it is drying these droplets, and it dries smaller and smaller, finally till it releases the positive ion, and all the solvents are evaporated, and you get the ion. And these are the curtain gas, as I told, the heated nitrogen gas, and the ions are sucked into the mass spectrometer. It goes to the mass spec. So this has to be very clear. Once again, it comes from the LC, it goes to a bilayer needle, as you can see here. This is an exploded diagram. There is a potential difference that we keep between this and that, minus 5 kV, and you can see the positive ions are formed inside. So this is a solution chemistry. There is no electron bombardment or anything like that. Also, it is a solution chemistry. In the droplets are full of positive ions, and when you come here and negative ions, we don't want the negative ions. We'll select the positive ions, we will separate them, we'll remove all the solvent front, and there is some gas coming from here. We'll make sure that no droplets are allowed to get into the mass spectrometer, and with the potential difference here, with a negative voltage here, the positive ions will be sucked in. I hope it is very clear to you. This is electrospray ionization. Once you understood this, then apna mutti mein hai. It is nothing complicated at all. People will talk electrospray is very complicated, very difficult for you to swallow and all that. I want to impress upon the students, there is nothing difficult. It is made simple, especially we have got all the slides today. The audio visuals are very clear. We need to explain to you. Once you explain to you, it is very easy. And once you work with the mass spectrometer, you will appreciate it that these things are very easy. So there is nothing difficult. Okay. What is more difficult is to the present day, how we are living in our conditions, but the mass spectrometer is much easier than living in the present conditions. So it is the droplet size reduction that we are working out. So the dissolvation, as we said, evaporation of neutral solvent and volatile buffers. You can use The advantage of HPLC is that compared to GC is that GC is limited to the number of gases or number of liquids. You cannot use liquids. So the mobile phase doesn't have any activity at all. As Professor Dattar explained to you, the advantage of HPLC is that the solvent front here really takes part in the separation. So here you can use volatile buffers also. Don't use non-volatile buffers. If you are using ammonium acetate, it is very good. But if you have got something like that, sodium phosphate, then replace that with sodium with ammonium, and you can say really half of the parts should be organic, and those type of volatile buffers you can use for LCMS. So you can have your methodology done in sodium phosphate, but when you come into LCMS, make sure you remove your sodium phosphate with the ammonium phosphate. Otherwise, you will find that all the orifice in the mass spectrometer is completely blocked by the sodium salts, and it will be very difficult. And the droplet vision caused by the electric repulsion between the like charges. So what happens here is very interesting. So when you have the positive charges, the droplets become less. Then when it becomes very small, the positive charges comes too close. So when they becomes too close, there is a Coulomb's explosion. It cannot stay very close to them, then they explode them. And that is called Coulomb explosion. And that is why where you get, that is called, there is a lot of technical terms of Rayleigh limit, etc. When you read the books, don't want to go into those complications. But mainly what happens is when it becomes smaller and smaller, the surface tension around these droplets becomes very high, and they cannot hold all the charges around there. So immediately what it does is that it just breaks up into positive ions. This is a beautiful mechanism. The mechanism of formation of the positive ions is extremely beautiful. So as once again I say, we form the droplets, and the droplets contains your positive ions. We are not interested in the negative ions unless we are doing negative ion mass spectrometry, and the negative ions will not be going into the mass spectrometer. The droplets become smaller and smaller. The only reason is we have the drying gas coming. The hot nitrogen gas is coming, and it is constantly drying the droplets. Well, when the droplets keep drying, they become smaller and smaller in diameter, and it becomes so small where the positive charges come so close to each other, they cannot hold each other together, and the same polarity one, they will just ripple. So the positive charges ripple from each other, and they will break into the ions. And that is the mechanism of electrospray. These are the 2 or 3 most important slides. If you have understood this, you have understood electrospray. So once again, I will repeat. Going back to the slide, this is very important. You have a bilayered needle. Your liquid component, your liquid from the HPLC comes through this bilayered needle. Outside you have the gases, you have nitrogen gas, and that will be sprayed, by like an aerosol spray into droplets. And there is a potential difference that is maintained between this tip of the needle and the frame of the ion source. And that gives an electrostatic field in order for the molecules to ionize. Okay, and the positive ions are formed. Some negative ions are also formed, but you are not interested in the negative ions in the positive ion mass spectrometry. And these big droplets are being dried by a drying gas. These are hot gases, and then all the droplets are become smaller to a limit, to a Rayleigh limit, where the positive ions are so close to each other that they are not able to close together. They are the like charges, so they ripple and they break open, they explode. The Coulomb explosion that is explained, and into the positive ions. So this is a beautiful mechanism, very simple to understand, and once you understand it, you put it in your mind and visualize it. These slides help you to visualize. So you can see charges become smaller and smaller droplets, and it explodes, gives you the positive ions which are sucked into mass spectrometer. So once you remember these slides, it will be very easy. I'll try to upload these slides or my talk into some media so that you will be able to follow that. I will try to inform you once I put into some media so that you will be able to follow. This is the first time I'm giving a talk in front of a computer. I am usually used to only the live audiences, but this is the first time I'm getting used to talking to a computer. Again, which is the same thing as you see here, and sometimes when you are using the biomolecules, you have to remember, if you are using the normal molecules, small molecules, that puts one charge on the molecule, so you get M+. Here it is not M+, I will explain to you what is actually formed. And then, if you are using a biomolecules, it will put multiple charges. That will also explain to you. So what is a single charged ion and what is a multiple charged ion? And here it is important to say now with this spectrum that with this slide, when you have the molecules there, here please look into that. You have the molecules and you have the protons here. Now the protons come generally from your solvent front. So you are using, let's say that you are using water, reverse wise you use a lot of water, or there will be always some water molecules present. And the water molecules will present a proton, or your solvent front will give a proton, or your buffer will give a proton or an attack ion, and the neutral molecule will get added onto this proton. And generally in electrospray you get M plus H plus. You must remember that this is the difference between GCMS ionization and LCMS ionization. That is why I said it's important to attend yesterday's session to understand this. In GCMS, what you do is that you remove one electron from the molecule, so you get a molecular ion, which is charged. So there is no mass added to it. So it removes one electron, so it remains, you get the molecular weight. In this case, what happens, it is a very soft ionization. There is no electron bombardment. So your neutral molecule acts with a proton which is present in the solvent, in the solution front, and that proton is transferred to the molecule to give an M plus H ion. So that is what is the process which is shown here. So around the neutral molecules, you have the H plus, and the H is formed into H, M and H. Now, if you have got a protein or a peptide, if there are some students who are working on protein or peptide, you can see that many nitrogens are there. And in all those nitrogens, what happens? One proton gets added. They really like to absorb the more protons, so many protons are added. So you get M plus Hn plus. That means every nitrogen has a H in that. So you get a really, what happens is that, I will explain to you, this is a multiple charged. So you get multiple charged ions. How to analyze a multiple charged ion is a separate beast. I'll explain to you. So first let me explain to people about the low molecular weight compounds, where it uses, generally it becomes M plus H, that is a molecular ion plus 1. So you get an M plus 1 ion. So this is the solution chemistry. Very, very important for you to know. Best suited to basic drugs, wherever there is a basic or HCl salt, then H plus gets added very easily. Okay. Sometimes what happens is comes from the H3O. The water can get becomes H3O, and that H3O can give an H plus to the molecule. And if there is a sodium, sometimes a Na plus can join into M. Is an example, Taxol, if you take, it generally gets added. And if you are using an ammonium acetate as a buffer, that is what I said, it's very beautiful. It may even either form an M plus H plus, or it may use an M plus NH4 plus here. And that is the beauty. So that is the type of ions. I should put a plus here, and here there is a plus like this. I should put a plus here. I will correct it today after the lecture. Okay. And then this is H3 should be down here. So the water which is getting protonated, and the protonated water can give an H plus to this. So this is how the mechanism takes place. So please remember, it is a solution chemistry. Sometimes people used to, without knowing the mechanism, people used to call it is a witchcraft. It is not a witchcraft. It is basically a solution chemistry. Once we know the mechanism, once we know it, it becomes very easy to follow. Again, organic chemistry comes to your help. The fundamental basic organic chemistry is very, very useful wherever you go, whichever walks of life you take. Organic chemistry is extremely important. I want to stress upon that. Whether you go into analytical chemistry, whether you go into biochemistry, any types of chemistry you go, organic chemistry, or you go into pharmaceuticals or pharmacy, any branch of the science you go into, the organic chemistry becomes extremely useful to you. And the negative mode, it mainly happens is it abstracts a proton. So when you have M, then it takes a minus, either a negative ion gets charged into it. So I will show you an example of that when I show RDX picture. So you can either abstract a proton. For example, you have an acid, COOH. It's very easy to abstract the proton from that, so it becomes COO minus. So then in that case, you will get an M minus 1. But if you are going to form an adduct of something onto that, like formate, then you will get a formate ion along with that. So there is a lot of chemistry for you to understand. But today, if you understand this much, I think you have done well, and you can do the reading. And with some more experience, you will see that you become an expert on LCMS. Don't worry about it at all. It's only a matter of time. All of you will become experts on LCMS. This I already explained to you. This is what I exactly explained to you, so let me not dwell upon that. Now, when you are talking about the electrospray, then the smaller amount of flow rate will be better to form that, because then nebulizing gas promote droplet formation, then volatile phases promotes, then it is better that less amount of solvent it has to dissolve it. Okay. Now let me not stay over here. Let me go to the most one. So it is good for soft, it is a soft ionization technique as I told you, and it cannot ionize non-polar compounds. That is the limitation of this. With a multiple ion charge, it is very good for proteins and peptides, and it is also good for some of the low molecular weight compounds. It is good for low molecular compounds, mid molecular compounds, and really the other ones which are proteins and peptides. So if it cannot, some of the non-polar compounds, if it cannot ionize, what do we do that? And that is our next section, which is called APCI. Or this is an example of L-salbutamol, and you can see that this 100 nanogram combination, and you can see the base peak of 240 mH plus. There is a nitrogen, so it's an odd molecular weight. So a proton is added to that, you get 240. Base peak corresponds to. And one thing that you should understand difference from GCMS and LCMS is, since it is a soft ionization technique, you will not see the fragment ions. So when you don't have fragment ions, you cannot do a structural identification, and you cannot do a library search also. So that is a limitation of LCMS. But how do you get more number of ions? How do you do this? That will be a part of LCMS&MS. I will probably try to end. I may go a little over time, but these lectures are supposed to be for 1.5 hours to 2 hours. We are trying to restrict to 1 hour, but we may not be able to do justice on 1 hour. But some of you participants have said it doesn't matter if you go a little over time. So I am taking the flexibility on that. And as such, you are seeing I am speaking much faster than what I would be speaking fast speaking when I am in a live audience. But I have to do that just to cope up with the time. But please remember that this is a soft ionization, so the M plus H plus does not have enough kinetic energy, so it will not fragment further down. So you will not see the other fragment ions. And that is in case a beauty about LCMS also. First you can get the molecular ion. If you want to know the fragment ions, you can do a collision activation, which is an MSMS, this will take me easily into an MSMS lecture. Okay, I mentioned about RDX. I was looking for a good slide of RDX, and you can see this type of nitro groups present in RDX. This is a plastic explosive, which is very, very bad. As I mentioned to you the other day when I was talking the first day, and I got a beautiful spectrum, and this is where I said this is a negative ion mass spectrometry, and a formate ion just gets added to it. It is always interested in electrons, so gets added to it. So it's a formate ion that you are looking at RDX. Okay, the molecular weight I think is around 222, and this ion gets added to it. So you see 267 and no fragmentation. Beautiful way to do RDX. So if you are in a forensic science laboratory, if you have to do RDX, then the negative ion LCMS is the best method that is applicable. Glycoside, when you can put a glycoside into a GCMS or anything, you have to have LCMS, and glycoside contains the sugars, as you know. These are the sugar part of it, and this forms beautifully a sodium adduct. So this is nothing but the molecular weight plus sodium adduct. So that is beautiful. So about 23. M plus 23 is this ion. So reduce 23, then you get your molecular ion. That is very, very important to you. So that is an adduct ion. Sometimes you may ask from where the sodium comes from. Sodium can come from your mobile phase. There can be some sodium impurity, or the most interesting that we have seen is that from glass, which is made by sodium silicate. The molecule can take a little bit from the glass phase, and that is enough for it to form a sodium salt. It is amazing. It's a real wonder and a mystery how sometimes you get this type of molecules, how they interact with these ions, and you produce that. But everything to our advantage. Every time I used to say, when you are talking about once upon a time, people used to think, why do you have all these things of deuterium, isotopes? Deuterium is there, carbon-13 is there, and it is all problem for us. If the carbon-13 is not there, it will be better. Why carbon-12 should be there? Why along with carbon-12, carbon-13 should be there? Those people who are doing today the NMR of carbon-13, they know the importance of the natural abundance of carbon-13. And so also deuterium. How important the deuterium is. It is very, very important, all these things which goes, there is deuterium NMR also. We can substitute a proton with a deuterium, and we can do a deuterium NMR. And I'm very happy that we have applied all these technologies in our research many, many years ago. So all these tools are available to you today, and nothing puts us back saying that I'm not able to do my research. Go to the national centers, go to wherever these facilities are available, and if the universities where you are working, colleges where you are working, you don't have a facility, make sure you go to the right institute. They are all government funded. Go and knock at their door and say that I want this, and get your stuff done. Be aggressive if you want to get your stuff done. I'm mainly telling this to students in the group. Now, this is very interesting, as I mentioned to you. When you take a biomolecule, then you put a multiple charges. What are these multiple charges? As I mentioned, if you take a compound which has got, let's say 30 nitrogens present in that, a peptide with 30 nitrogen, every nitrogen atom you can put a charge. So you get a multiply charges. There may be a combination of 30 groups of ions that is present. Not that every nitrogen in a peptide gets protonated. In one, it gets the first one, second one, third one. So different molecules get protonated at different places. So you get a combination of ions of all these. So that is called multiple charge ions. And when you see a multiple charge ions, then you will see it is something like this. And this is from one single compound you are getting this. So this is very complicated. This is not a mass spectrum. This is you can say this is mass spectra. This is a combination of mass spectra, but then we want to know what is the molecular weight of your compound. And if this is myoglobin, we will see what happens. The software is very important. That is called the deconvolution software. And this protein is analyzed to this extent to this decimals that we can get accurate. None other method in biology could get the molecular weight to that accuracy. So you can get here 26,828.84. And they can also the deprotonation, protonation, demethylation, all these type of things, phosphorylation. The biochemists could see all those things using the mass spectrometer. It became a beloved part of their instrumentation. That is how the biochemists really embraced the mass spectrometry. Today, a biochemist cannot live without the mass spectrometry. Any paper that they publish, you will see a mass spec there. Any conference that you go in mass spectrometry, 60 to 80% of the papers are taken by them. And the small molecule people, pharmaceuticals and other people who are dealing with LCMS or small molecules, they get about 20 or 30% or 40% chance to present papers. That is the world today that we are living in. It has become so popular. Without Electrospray and APCI, we cannot work. Now, when you come to APCI, the Electrospray has a limitation. Some of the low polar compounds, it cannot ionize. So in that case, what we do is that we heat. The probe is heated. It is still biolaminated needle, but there is a heating around that needle, and that heats up the molecule. And when it comes out, it is with the nitrogen gas, it is a heated molecule. We put something like a corona needle, and there is a voltage applied between the needle and this surface, and around the needle, the ionization takes place. So it's called it is not a coronavirus, it is a corona needle. There is no virus here. Okay, so you get an ion plasma here. So at the tip of the needle, what happens when the solute comes here, it is under the electrostatic difference in the field, and then it is heated also, and here at the tip, it gets ionized. So here the mechanism is, so this is what it is. This is the heated probe, and this is a needle, and this ionization takes place here. Ions are sucked into the mass spectrometer. I'm happy. These are the instruments. I have actually used them, so I'm able to get some pictures to share with you. These are not taken from literature. These are actually taken from our lab at that time from the United States. So here what happens is here, now it gets heated up and the molecules get ionized here, and then you get the M plus H plus. So the mechanism here is very simple. It is like I said, what did not do the chemical ionization in GCMS. I did not have time. And here also I cannot go back to GCMS right now. But here what happens is in Electrospray requires less amount of flow of your mobile phase, whereas APCI you want a little bit more. So if you want 500 microliter in Electrospray, you can take up to 1 milliliter in APCI. And the advantage is that if you are using methanol as the solvent front, for example, for low molecular, you will have an organic phase. So the organic phase, what happens is the methanol undergoes the protonation. So as you can see, SH, S stands for your solvent front. The solvent is S. So the solvent front gets a protonation. So if it is a methanol, it becomes, instead of CH3OH, it becomes CH4OH, a proton added to it. And that really mingles with your molecule and gives a very friendly transfer of one proton to that. So the solvent molecule, which is solvent, which is protonated solvent, transfers one proton to it, it becomes MH plus. That way, some of the low polar compounds, you will be able to really ionize them. And that is the principle behind APCI. So APCI is no beast. Once you know API, which is electrospray, and API is a general term, atmospheric pressure ionization. When you are doing it, the conditions I explained with the electrostatic difference and all that, that is called electrospray. And now APCI is a variation of that. Okay, so here you are applying the voltages. For example, reserpine. You cannot imagine being reserpine doing with a GCMS or so. So you need to have this. This is about 600 plus molecular weight, you can see, and this is reserpine, and reserpine M plus H, you can do very well with APCI. You can do this with the electrospray also, but APCI is very, very good. In fact, to tune the mass spectrometer, we sometimes use the reserpine. A reserpine is a natural product, you remember, from Rauwolfia, we take it from the root of this plant, and reserpine is a very, very important compound in tuning of this mass spectrometer. And also when you go to protein molecules, we use myoglobin in order to tune the mass spectrometer. Once it gives myoglobin very well, then we can say the mass spectrometer is in good condition and we can use it for other molecules. APCI mechanism, I already talked to you that it is transferring one proton from the protonated solvent front into the molecule. APPI is even very interesting. Even some of them which are not amenable to APPI, which are absolutely no way to to do them, then you say photoionization. Now many of the companies are selling this. Again, it comes from here, from this tube. It's a heated one, and it nebulizes here, and then there is a UV lamp here which brings out these photons here, and that becomes ionized. And these are used only for certain type of compound, this type of compound, which are not even cannot be ionized by some other technique. So this type of things and acetone, etc., they are very good candidates for that. So photoionization works very good for this. So what are the basic types of this thing? How do we choose the type of ionization? As I mentioned to you during my talk, as long as you can do with an API, your low molecular weight compound, so it is not thermally labile. If it is thermally labile, and if it is the higher molecular weight compounds like proteins and peptides, you can use electrospray. And from some of the non-polar compounds that you want to use a little bit of force on it, you want to heat it up, and then you can want to do that, then you will do APCI. And with the very low polarity compounds, which does not work in APCI condition also, then you can APPI. So your choice of this should be must is electrospray, and I will say second you will go for APCI, and the third will be APPI. But if you are working always on the type of compounds which are working on APPI only, then you will go for APPI instead of APCI. So it is your choice. So depending upon your molecule, you will choose what it is. So generally, if you go for an LCMS, if you can afford only one interface, then definitely go for API, which is electrospray, API electrospray. Now the choice of this. Now this is a very important slide which I have drawn here. Now this is the electrospray, and this is the electrospray ionization, which is the high polar compound, and this is less polar compound. This is on the negative polar, and you can call it positive polar, you can call it. And EI is very good here. APCI works here a little bit here. APCI works here, and for some of the normal compounds, the electrospray is very good. Abuse drugs are some examples only. Here, as you can see, you can get as good as your GC separation when you do the LC separations also. And at each peak you click and you get the mass spectrum. Here it is a little bit more fragmentation, and that doesn't happen mainly in this one. So it could be either a mixture. You have to see that when you get something like that, you have to even doubt about it, that it could be a mixture. But if such a spectrum you can get from LCMS&LCMSMS. And this is the quantitation. You can do a very good quantitation. I'm not going through details of that. So this is the triple quadrupole, Q1, Q2, and Q3. Instead of one quadrupole, you have three quadrupoles. And the middle quadrupole is not something that you can scan. It is called a reaction cell. It is called a collision cell. So you can see that Q0 can be a filter. It doesn't have any field here. So the ions which are produced here are coming over to here Q1 and goes through Q2 and Q3. So what happens is Q1, you can see the advantage of an MS/MS is that in the Q1, you find out what is your molecular ion, and you tell that I want to go the molecular ion of this compound to go through that. And when the molecular ion comes through that, let's say cocaine. So 303 is the molecular ion, and it goes through here, it comes here and you impinge with some argon gas or helium gas, and this is a collision cell. So in the collision cell, they undergo fragmentation, and once it undergoes fragmentation, these fragments are pushed onto this. So when it comes to Q3, so if it is cocaine, then cocaine contains the 272, 182, 82, etc. here. And it will scan according to the mass to charge ratio, and you get your mass spectrum here. So the advantage here is that if you have got a very impure sample here and you are not able to do a sample preparation, you can say that I'm interested in this particular compound to go into here. So if you have a mixture of, let's say, cocaine and with the 2 or 3 other compounds, you say that I am interested only in cocaine and go through electrospray. All the ions of different compounds are formed, but it will let in only one ion, which is 303. It comes here, gets collision, activation, dissociation, and it goes all the ions of cocaine, and then you see the mass spectrum of this. So that is what you say MSMS. So the advantage of MSMS is tremendous. And now when you go to bioanalytical, there are many people in the bioanalytical. You have a dirty sample from the blood, and from the you do some sample, but still when you take it, the sample is very impure. So do the MSMS of this dirty sample, but the compound of interest, you focus on that ion and bring that ion and you decompose here, and you can see the spectrum here. So you can see the bioavailability at different times you can see. And if you want to see the metabolite, you can also concentrate on the after this dissociation, you can concentrate on the metabolite. So if a molecule is coming here and you want to see the metabolite B of that, then you say, I want to concentrate only on B and see whether B is formed or not. So from one ion, if you want to see from A, if the B is formed from A, send A, do the dissociation, collision dissociation, and scan on B only. Let the quadrupole stay on that. So if I want to see 182 came from 303, I will let 303 go here, and dissociation here. I will tell this quadrupole, you sit here on 182. So quadrupole will say, yes, I am seeing 182. So you can say that 182 came from 303. What a beautiful mechanism. What a beautiful mechanism. Put your thought, very basic thoughts. You will see that it is very simple. And there are many things you can do with the quadrupole ionization, triple quadrupole. I am touching on one or two. There are neutral losses and other applications and all that. I am not going into the details of that because triple quadrupole MSMS is a separate lecture by itself. Okay, and that requires really some competent people who have done a lot of work on that, and they will be, if they are bioanalytical, we have to bring out some bioanalytical people and talk to you how the triple quadrupole is used on that. And they will give you all the details of that, and we will definitely arrange some talk how to do that. Ion trap, I am not going to go into ion trap, but this is a 3-dimensional ion trap. There are 2-dimensional ion traps, and they are also very good in impurity profiling. So I think my idea is not to go to ion trap. Let me stay with the triple quadrupole today, and you can do that also for myoglobin. So there are, as I said, there are so many different types of analyzers. As I said, Orbitrap is one of the latest. The last 20 years, if you see what has been a very important development, then it is Orbitrap, which many people are using. India is also blessed with having so many Orbitraps here. There are several few $100,000 it costs, but it can do low molecular weight compounds, high molecular weight compounds, biological molecules, everything. So if you have plenty of money, if you are sitting on that, it is a Orbitrap is a very good instrument to go for. But wherever you have application, make sure what is your application. If it is bioanalytical, triple quadrupole is very good. If it is qualitative analysis, structural elucidation, both ion trap, is very good because you can do MS, MS. I have not gone to the details of that. You can look at that. There are variations of that. There are Q traps also. Quadrupole, that is all, really hybrid mass spectrometers. You have the TOF combined with the quadrupoles, all types of permutation combinations today you can get, and everything has a particular application, particular advantage. So I want you to look at that. So I will, in short, bring to you a summary of what we have talked. We have talked today electrospray ionization, which is a soft ionization technique, which is applicable to low molecular weight and thermally labile compounds, and also very high molecular weight compounds, that is proteins and peptides, and non-volatile compounds. If you have non-volatile compounds, they are good also to work on ESI. And some of the non-volatile compounds and some of the low polar compounds, they will not work on ESI. So you need to put a little bit of heat on it, then you have got APCI interface. So APCI interface I have discussed with you. I have shown some molecules where APCI is very useful because you are heating the solvent front as well as this one. And mechanism, I have told you that it is basically the sample molecule, this is the solvent front undergoes ionization, or the water which is undergoes ionization, and there is an H3O and which can give a proton in electrospray. Or if you are working with the sodium is around there, it can form an adduct ion of Na plus. If you are using ammonium phosphate or ammonium sulfate, or not all sulfate acetate, then it can form an ammonium adduct onto that or give a proton to that. So there are very few, there are many forms of forming an ion. So formation of an ion is very important in LCMS. Formation of an ion is not a challenge in GCMS. GCMS, you can blindly send the compound into the ion source and impinge electrons on it. So anybody without much experience can do a GCMS. But when you are doing an LCMS, you have to really understand what is your molecule and what is the methodology that what you want to choose, and what is the things how you can ionize it. So do not see when you are having a protein peptide or an enzyme, etc. Oh, I have got APCI, let me do APCI. Wrong decision. So I am requesting you, all of you, please look at the sample. When somebody brings a sample to you on LCMS, even if you are an LC, you have different LCMS in your lab, please see. That is where I say the organic chemistry a little bit helps you to your strength. That look at the molecule and see what will be amenable to you. Even if you have all the things available to you, first to try the sample on ESI. That is the first thing you can try. If it works on ESI, nothing like that. If it does not work on ESI, then you see whether it is necessary for you to do APCI. Then you do APCI. And if it doesn't work on APCI, go for APPI. Now the point is that if you are working with biological molecules, don't go for anything else. Straight away go for ESI only and optimize the ESI parameters so that you get the good peptide spectrum or good protein or whatever you have. And you can digest some of your proteins, get the peptides and analyze the peptides also. You know that aspect of it very well. So whatever you need to do, whether protonation, deprotonation, whatever you want to see, you can do with LCMS. With LCMS. You can have LCMS attached to a single quadruple mass spectrometer, and you can get attached to a triple quadruple mass spectrometer, and so on and so forth. But right now, single quad is the minimum that you need in LCMS for your LCMS to work, and then you can go to triple quadruple or for any hybrid mass spectrometers.